Hi friends, happy morning. Today we are going to discuss two important theorems that we are using in vector calculus, right? First one is divergence theorem, second one is Stokes theorem, right? So let us start with the divergence theorem, right? So divergence theorem. See, this divergence theorem and Stokes theorem we using for converting one kind of integral into another, right? So here an areal integral, right? That means a surface integral we convert into a volume integral, right? In divergence theorem says about a conversion of surface integral into volume integral, right? So first of we can see what is the statement regarding divergence theorem, right? See, suppose you have a surface integral a dot dA. That means suppose a vector field A, we are taking its surface integral. That is equivalent to volume integral, but we should take the divergence of that particular vector field. Then the areal element you can change into volume element d-tau, right? Basically this is the divergence theorem, right? Where we use divergence theorem, right? In electrodynamics, during the calculation of electric flux, right? See, surface integral of E dot dA. This is what? This is basically electric flux, right? To calculate this electric flux, we can use in volume charge distribution of charge density is given. We can simply calculate the flux using this formula. Once you get flux, that is helpful to find electric field. Once get electric field, that is helpful to find electric potential and all, right? So we apply divergence theorem and we get the differential form of Guass'S theorem, that and all we study there, right? All right. So basically this expression is this. Now through a problem we can try to prove this, right? So let us go to a problem. See, here one problem is given, right? So here, see, look here, check the divergence theorem using the function. Here a vector field is given. What is that vector field? A is equal to y square x cap plus 2xy plus z square of y cap plus 2yz z cap, and the unity cube situated at the origin. So suppose you have a cube, right, that is situated at the origin, and the side length of the cube is unity, that means 1, and suppose that field, this particular field you are applying to that cube. Now the divergence theorem valid or not, you can check. First we find out the LHS of divergence theorem, then we find RHS. If both are equal, we can see this divergence theorem is valid, right? All right. So let me write this vector field first, right? So see, look here, I considered here a cube, right? Then to this cube, so this is situated at the origin and the side length of this cube is 1, right? Now here I am applying this vector field. This is the vector field given in the question, right? Now basically what we do, as per the theorem, what we studied, integral a dot ds, right? The surface integral that should be equal to divergence of the vector field into volume element, right? That is we studied dV. This is the divergence theorem. Okay, so to calculate this A dot ds, right? So for a cube, how many faces we have? We have 6 faces, right? So it is very difficult to find the surface integral. Why? We have to find each face surface integral and we have to sum up. Then only we get the complete surface area. So complete surface integral of this particular field. Alright. So mathematically we are doing all the areas. Suppose look here. First I am considering this area. Right. What is this area? This area is projected along the y-axis. So the direction is y cap. Area direction is normal to this surface. Normal to the surface. Alright. So here this y cap is the direction. So to find the surface integral of this particular area, see this is along y cap. You should take the function this y cap directed function. Right. Then what is surface integral of this face? Integral 0 to 1? 0 to 1. Because both x and y, here look here, this dx, right, y cap, the area direction is y cap, then this is dz, right, and this is dx, alright. So dx dz is the area, right. I am calculating this part, right. Then function along y cap I taken 2x plus z square and dx dz, right, that is the area along y cap direction, right. Now this face is situated at a y is equal to 1 along the y axis. See, y is equal to 1. So I am replacing this y as 1, right. Then 2x plus z square dx dz. Now I can integrate this 2x square by 2 dx. First with respect to dx I am integrating, then 2x square by 2, then z square you can treat as a constant, z square x, and I am giving the x limit of integration 0 to 1 dz. Now this 2 cancel, and by giving 1 to the x variable, right, 0 to 1, then 1 plus z square dz. Then again integrate with 0 to 1, then z plus 1 dz on integration, z plus z cube by 3, again give 0 to 1, then 1 plus 1 by 3 come 4 by 3. Alright. Now, so this face area we got. Now what is this face area in this direction? That is negative, right, negative of the same area come, but it is in the opposite direction. So negative of 0 to 1, 0 to 1. But one condition here, y is equal to 1, here y is equal to 0, right. Y is equal to 0, here y is equal to 1, here y is equal to 0. So when I put along the y cap y is equal to 0, this first term will be 0, alright. This 2xy, this y is equal to 0, alright, that means z square only. So z square, same dx dz only, right, area element. But there is a negative sign, this area projected in this direction. Then z square, first you apply this z square dz, right, that is z cube by 3, right. Then z cube by 3 dx on integration x is 0 to 1, that is again 1. Then z cube by 3 you give a limit 0 to 1, 1 by 3, then outside minus minus. Now, so we calculated this area and this area. Now you can calculate this area, right. This area is projected along z cap. Then which component? This part of the function we will take 2yz. Here z is equal to 1. So what I write? Z is equal to 1 means 2y is the function, and this area is, this is y axis limit, then dx, this is x, so dy dx, right. So this is dy, alright, this is dy, and this is dx, right. So dx dy, right. z is equal to 1. So z cap direction means this part of the function, right? So dx dy, what? 1, alright. How 1? This is y square by 2, then 2 to cancel, y 0 to 1 is 1, dx on 0 to integral x, integral dx is x, 0 to 1, again 1, so result is 1, alright. Okay. Now what about this? This is minus z cap direction, z cap direction is this only, but here z is equal to here 1, right? Here z is equal to what? Here z, this point, at this point we calculate z is equal to 0 at the origin, z is equal to 0. That means this function z is equal to 0 means this won't exist, right? So that means this integral of this field 0, right? Now we want to calculate, so let me erase this first. Alright. Now again we focus on this part. This is x cap, right? This direction is x cap, this area situated, right? So x cap we take y square as the function, alright? So here y square and this area is along the x cap, then dy dz is the area element, right? Because direction is along x cap. Then you will get a y cube by 3 and a dz 0 to 1 y square dy, that is y cube by 3 integral, then 0 to 1 1 by 3, right? Now what about the opposite area there? X is equal to 0, right? X is here 1. Then this backside area, if I choose this area, I am speaking about this area, right? This backside area, right? So that is again the function is along x cap, that is y square, but this area projected backward, that's why there is a negative 0 to 1, 0 to 1. Function is again y square, x is equal to 0, doesn't affect this function, dy dz, then minus 1 by 3 come, right? So now I calculated a surface integral of the vector field throughout all the 6 phases, right? Now what is the net surface integral of this vector field? See, here 1 4 by 3 there, here minus 1 by 3 there, here plus 1 by 3 there, this and this cancel, alright. Now here 1 is there, here 0, then 1 plus, right, 0 plus, here 1 4 by 3, and here again minus 1 by 3, then 1 plus 4 by 3 minus 1 by 3, again 1, then answer is 2, right? So the complete surface integral of this vector field through that cube situated at the origin is 2, right? Now what you understood from this calculation? This calculation is very complicated, right? That's why we employing Guass'S divergence theorem. According to Guass'S divergence theorem, see this particular integral a dot ds, instead of calculating these, you can calculate this only, right? Integral divergence A. So how we calculate it? So I will show you how to calculate this, right? Okay, so see what we studied, a surface integral divergence of A. Instead of calculating this surface part, I am calculating this side. So we already got the answer as 2. Now let us check, very simply we get the same answer to divergence of dV, right? What is divergence of this function? See, divergence of this function is that we can find out first. Divergence of A is, that is dou by dou x of y square, that is 0, dou by dou y of 2xy, that is 2x, and dou by dou z of 2yz, that is 2y. Then what is divergence of A? 2x plus y, 2x plus y, alright. Now I am substituting these, right, integral, so this is volume integral, so integral 0 to 1 for a cube x, y, z coordinates varying 0 to 1, 0 to 1, 0 to 1. What is this value? 2 into x plus y. What is volume element? dx dy dz, right. Now calculate these two I am taking out, and first with respect to x I am doing x square by 2 plus yx 0 to 1. Now keep the remaining two integral limit here, right, and dy dz here. Then what will you get? X1 here again x whole 1, then 1 by 2 plus y. 1 by 2 plus y again I am integrating, then 0 to 1, 1 by 2 with respect to y I am doing, then 1 by 2 plus y, then that is y square by 2, then only remaining 0 to 1 dz only, alright, dz only remaining. Now 1 by 2 y, if you give limit, what come here, integral 0 to 1, see this is y1, then 1 by 2 plus 1 by 2, that is 1 dz, right. See, look here y square by 2, then 1 by 2 y plus y square by 2, right, 0 1, then here putting 1 by 2 plus 1 by 2, what, again 1 only, right. Now we have dz here, alright. So we have one outside 2 here, that is keep here, right. Then 2 times, this is 1 dz, then 2 times dz on integration z, limit is 0 to 1, then 2 into 1 minus 0 is equal to 2. So by applying the divergence theorem, the right hand side of this divergence theorem, you get the same result too, right. Alright. So this is all about this section. This divergence theorem is helpful to calculate complicated integral. Similarly, Stokes theorem also very important to calculate the problems. Alright. Thank you.